Okay, so we'll continue with the optimization of functions of two variables. Yesterday we finished our first example, which was related to the paraboloid, the surface of revolution. And today we will do some examples that are either theoretical or more applied. So the next one is related to find all the critical points for the function 12x minus x cubed minus 4y squared, and we have to classify each one of them as either a relative maximum, a relative minimum, or a saddle point. So, well, in order to find the critical points, we need to find the partial derivatives, f sub x, which in this case you have 12 minus 3x squared, then f sub y, these two depend on x, so you ignore them, then you have minus 8y, and you would equate for the critical points, the partial derivatives fx and fy are 0. So, well, that would mean on this hand that y is equal to 0. And then, well, basically you have x squared equal to 12 over 3, 4. So that means that x is equal to plus minus 2. And with that knowledge, that means that the critical points are of the form plus minus 2 comma 0, right? So again, can you see clearly, or if it's too bright? Yeah, right? Well, sorry. That's not the very well. It's the same, isn't it? You went to the other extreme. Okay, we will have to do with it. Basically, it's the second scale in terms of the brightness. I think that's okay. So, let's see. Yeah. Okay, so we found the critical points by equating the partial derivatives to 0. And, well, now we need to apply the second partials test, if you remember, where we studied the function d of xy. Most probably the d was because, as you saw yesterday, it came from a determinant, where you have fxx times fyy minus f of xy squared, because fyx is equal to fxy. So that means that we have to compute the second partials, right? So fxx, so this thing would vanish. So you have minus 6x. Then you have fyy equal to minus 8. Then, as you can see, well, fy doesn't depend on x, likewise fx doesn't depend on y, so fxy is equal to 0, in the same way that fyx is equal to 0. And if you compute this, so far so good, right? So you would do the computation of these two, knowing that this one vanishes. So you have 8 times 6x with the minus gone, you have 48x. So, of course, you have to make the evaluation of d at these 2 points, right? So, basically, d evaluated at plus minus 2 comma 0 would be 48 times plus minus 2. So, for one of them, you will be negative and the other positive, right? The one that is negative will give you the saddle point. For the others, you need to study further to see if you have a relative maximum minimum. So just to put it clearly, well, basically the 2 comma 0 is 2 times 48. We just care about the sign. D of minus 2 comma 0 is equal to minus 2 times 48. So this one is negative. So in that case, you have a saddle point. At this point, everybody's with me, right? You guys remember from yesterday? So when D is negative, you have the saddle point. When D is positive, you have this positive definite thing. And then you study further, especially the sign of fxx, to see if you have a relative maximum or minimum. Well, basically, this one is greater than 0. So for this one, we know that saddle point exists as minus 2 comma 0. Then you have fxx, evaluate, for example, at the point 2 comma 0, which is minus 6 times x, which is 2, which is negative, right? So, and you also know that the evaluated at 2 comma 0 is equal or is greater than 0. So here what you would have is a relative maximum. If you remember, well, you have x squared, the parabola, okay, derivative 2x, second derivative 2. There you have the minimum. If you have minus x squared, if you do second derivative, you have minus 2. So this would resemble this case. So here you would have a relative maximum. But else to add? Well, of course, at the point 2 comma 0. And here the signs would give you the saddle point over here. So having found the two critical points, which are plus minus 2 comma 0, one of them is a saddle point, which is minus 2 comma 0. The other is a relative maximum of the function. Okay? It is mentioned in the book that, well, if you have forgotten how to solve systems of equations, especially systems of two equations for two variables, try to refresh by checking the appendix. Of course, linear equations, I'm pretty sure that you remember, or at least you get the gist of it. It might not be necessarily linear, so you might want to refresh your algebra. But the important thing is the procedure. Find critical points, evaluate this function D. At the critical points, check the sign. If it's negative, it's a saddle. If it's positive, you have to further evaluate, for example, with fxx to see if it's negative. Actually, you could have seen from fyy, which was already negative, because basically what you're doing is studying the direction only in the y direction. The change only in the y direction, which would be negative, and would further confirm that you would have a relative maximum. Okay, so is the procedure clear? Yeah? All right. So let's continue with the next example. So they get progressively more complicated. Just keep that in mind. And example 7.3.3 is to find all the critical points for the function of x and y, x cubed minus y cubed plus 6xy. And again, classify each critical point as a relative maximum, relative minimum, or a saddle point. So far, so good? So, well, remember this function. We start evaluating fx is equal to 3x squared plus 6y. Fy is equal to minus 3y squared plus 6x. If this is equal to 0, in order to find the critical point, well, you can pass, for example, this one, right? So 6x is equal to 3y squared. So you have x equal to y squared over 2. Then you can plug in back in here, for example, that would mean that 0 is equal to 3 times x squared, but we know that x is equal to y squared over 2, which is squared, plus 6y. So you have 3 times y to the 4th divided by 4, plus 6y, and all this is equal to 0, which would mean if you multiply by 4, that 0 is equal to 3y fourth plus 24th y. That can let you factorize 0 equal to y, 3y cubed plus 24th. You could even factorize the 3 if you want. So this is y times 3 times y cubed plus 8. And that should be equal to 0. So that is actually further clarification, because one possibility, of course, is that y is equal to 0. The other possibility is that y is equal to minus 2, because minus 2 cubed is minus 8, and this vanishes. Right? For each case, knowing that x is equal to y squared over 2, you have the solution. So x would be equal to 0 in this case, and then x in this case would be 4 divided by 2, which is 2. Right? So again, this one was not a linear equation, was basically, we have some polynomial, which is cubic, but it's easy to factorize. So you just play with your algebra and you're done. So the first critical point would be 0, 0. The second critical point would be 2 minus 2. Here you have a cubic, so you're done. And yeah, okay. So is there any question at this point? No? You guys saw the methodology? Critical points, partials equal to 0. Then, depending on how easy or how complicated the equation is, I'm at the mercy of the algebra and of the difficulty of the problem. In this case, it was not so hard to solve, so I got the critical points. And now we have to evaluate again this function, right? So, well, since maybe I'll write this first, so this is important. D of xy is again fxx times fyy minus fxy squared. Let's do the computation. So now we see that we actually need that. Fxx, so this is 6x. This term vanishes. Fyy is equal to minus 6y. You actually have some fxy, which means that first you take partial with respect to x, then partial with respect to y. The only term that would survive is 6, which happens the same fy, partial with respect to x. This doesn't count, you have the 6, right? So further confirmation that in simple cases the mixed partials coincide. You can do the plug-in at this point. So this would be, do the multiplication, you have minus 36xy, and then minus, and then you have 36, okay? So actually, let me put it in a more polished form below. E of xy is equal to minus 36 times xy plus 1, okay? So, of course, now I have to evaluate the sign at the critical points to determine what is going on. So, for example, the first critical point, so, well, let me make a mention here. Critical points are these two, 0, 0 to minus 2. Now, d at 0, 0, this term vanishes, and you have minus 36, which is negative. In that case, you have a saddle point at the origin. Now, let's say that you have the other point, 2 minus 2. So actually you could go back. Well, so minus 36, this is minus 4 plus 1. But you can actually, well, you have 36 times 3. So you have minus 3 minus blah, blah, blah. You have the plus. The important thing is the sign. In this case, you know that you are at the potential case of a relative maximum or minimum. But for that, you have to evaluate fxx or fyy. Now, fxx at the point 2 minus 2 is 6x, which would be 12, which is greater than 0. So in this case, you have a relative minimum. That can also be confirmed if you compute fyy, because y is minus 2, and if you multiply, fyy is also positive. So even regardless of the x or the y direction, you get something that behaves like a parabola in that. So let's see, what else am I missing to mention? Well, again, so these problems have the same structure. If you think about it, first step, find critical points, meaning that you have to find the partials and then equate them to 0, and then to solve a system of equations that give you the critical points. Once you know them, you want to figure out what is the behavior around the critical points which is for which you compute this D, which comes from a determinant, which has this form. Once you do the computation, but you need to compute the second partials in order to figure this form. You do the evaluation of the function D that you obtain at the critical points. The one that is negative is a saddle point. If it's positive, you need to evaluate the sign, for example, of fxx. If it's positive, it's a relative minimum. It's, again, using the table that we presented yesterday. Is the procedure clear for everybody? Yeah? Is there a question? Okay, look, try to review your notes, try to see how the steps are done. What I hope is that the presentation that I'm giving matches the step-by-step procedure that I mentioned in last class. Is that happening, or is there a question? Are you guys clear about the procedure? Yeah, okay. So we go to an applied problem now, which, okay, I will need a new sheet of paper. Okay, now we're going to use what we have learned to work in some business problem. So the problem will be related to maximizing profit. And the description is a little bit long, so bear with me, but the problem is interesting, even from the business point of view. So you have a store that has two brands of cat food. There is a local brand that is basically obtained at the cost of 30 cents per can. I thought I was going to use more space, but not. And then you have a national brand that is obtained at the cost of 40 cents per can. So that's the price at which, let's say you are the store, right? So you buy from the producer, or whichever, and then you're going to sell it. This is the price, such as if I'm the store, I buy it from the provider. Later on, of course, I will want to make a revenue by selling it higher to the consumer. That's the way it works. And that price I have to specify. And then I will find the profit by making a comparison between my price and what I bought it for. So then what I'm going to specify is the price at which I sell it. So if the local brand is sold, meaning by me, the store, for X cents per can, and the national brand is sold for Y cents per can. Now, somebody made a study. Let's say that I'm, I don't know, Walmart in a way, and I have like the head of intelligence of my business, and it gives me the function in which I will sell for the price of the products, right? So approximately 70 minus 5x plus 4y cans of local brand, and 80 plus 6x minus 7y of the national brand will be sold daily. Somebody provided me that information. So the question is, how should we price each brand to maximize the total daily profit? And there is, well, just a clarification. Assume that the largest daily profit occurs at a relative maximum. So the solution goes like this. If I want to define an equation for the total profit, or at least a function, which we will call f. So just keep it in mind. First of all, I have the factor x minus 30, because that's the difference between the price I bought it and the price I will sell it. And then 70 minus 5x plus 4y. So this is the profit that I get per item. And this is basically the number of items sold. Let's say daily. Now, on the other side, for the national brand, I also have this difference between the price to which I sell it and the price to which I buy it. And then, which would be, okay, this factor is the profit per item. And then the number of items sold, which is 80 plus 6x minus 7y. And, well, of course, that at this point you already know what's going on. This is the profit obtained from the local brand. And this is the profit obtained from the national brand. If I do actually the algebra and the computation for these two plus addition, the actual function that I would obtain is the following: minus 5x squared plus 10xy minus 20x minus 7y squared plus 240y minus 5,300. So I will let you verify that. I won't do that. But at this point, having written the function for the total profit, meaning local plus national profit, I can apply all the math that I learned. So under the assumption that the maximum occurs at a relative point that I can find with my criteria, the procedure is the same. Find the critical points, evaluate with this function d, which you can call a determinant or a discriminant. Well, it's a determinant actually. To find if it's a saddle point or a relative, either maximum or minimum, hopefully maximum. Once I do that, verify with the criteria to see if it's actually a maximum, and then that would be my solution. So we proceed with our computations, right? So fx, this is minus 10x plus 10y minus 20. All this depends on y or is constant, so I ignore it. Fy, this term doesn't count. Then you have 10x, this doesn't appear. Then you have minus 14y plus 240. So those are the partials. In order to find the critical point, I have to make them equal to 0. So this is actually nice because this is a system of equations in two variables, and it's linear. Moreover, I mean, for the algebra-oriented people, actually if I add these two equations, these will disappear. So I can do that, right? Let's say that I add this equation with the other equation, I would get is 0 equal, this cancels out, so minus 4y, and then plus 220. So that means that y is equal to 220 over 4, which would be equal to 55. So you have 50 times 4, 200 plus 20, etc. So, I mean, this was a strike of luck. We got lucky in the fact that if I add these two equations, the x variable disappears, right? Well, you guys have seen this if you have done systems of equations before, I'm pretty sure. And we were lucky. It does not necessarily happen, but okay, let's use what the problem has given to us. Actually, this could be reduced even more because you have divide by 10. So 0 is equal to minus x plus y minus 2, right? Everything has a factor of 10. So which would mean that x is equal to y minus 2. But since I already know that y is equal to 55, the x is equal to 53. And wow, okay. I mean, I could have written the system of equations in a matrix form, blah, 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 and look invertible, do Gaussian elimination, whatever. In this case, the equation was so easy that I could just, by simple algebra, go straight forward. So this is telling me that the critical point is equal to 53, 55. It's the only one. which makes sense because you have two equations, so then basically, yeah, you have two lines that cross and give you a single point. So that's a critical point. Now, of course, we have to do the evaluation of the criteria for which we need to compute the second order partials. So f x, since I already did the computation over here, so this would be minus 10, nothing else matters over here. F y equal to minus 14. Then if you want fxy, so now we consider partial with respect to y of fx, this would be 10. And if you want to verify fyx, of course you would keep this term. So you would have fyx. I mean, that we know already happens, but it's just confirmation for the function. Sure.
Can you explain how you get f, x, y, y?
Yeah, so keep this in mind. Okay? I equated them to 0 at the beginning, but I did the computation for fx and fy. So maybe the notation will help. fxy means that you apply the partial with respect to y to the partial with respect to x. So there's an order, right? Sometimes it's confusing depending on the notation, but this means that first you apply the partial with respect to x. Then you apply the partial with respect to y. So keep that in mind. I have this object, then I apply the partial with respect to y. When you apply partials with respect to y, you regard the x as constants. So this would not appear. This would not appear. You have the 10, right? Now for the other, if you have fyx, partial with respect to x of the f over dy. So would be this. Wait, did I make? Yeah. So you have this object, then partial with respect to x, only this term. This would be constants. And so you would. Is there another question? Let's see. What else do I have to mention? Well, okay, so this is just an example in which you have, again, this equality of the mixed partials that you know for well-behaved functions. Now you need to study this function, fxx, fyy minus fxy. So if I basically plug in, well, minus minus, you have plus 140, minus, and then you have 100, so you have 40, which is greater than 0. So that is nice. I mean, the fact that we got basically a quadratic function made the things very simple. And for this one, when it's positive, you have to study the sign of fxx in order to see if you have a relative maximum or minimum. So in this case, you have that this minus 10, so this would be a relative maximum, which is what you expected, because this is less than 0, right? So, I mean, if you forget, think of the parabola as x squared or minus x squared. Which one has a minimum and which one has a maximum? The same thing over here. So, well, that confirms our suspicions that at least this function is maximizing a profit. That would happen at the point 53,55. And, well, I mean, yeah, there are many things to say. It's actually an absolute maximum. Well, the function is extremely well behaved, so, I mean, can I explain it? Either you go to infinity, or because the domain is the whole R2, so if there's basically a local minimum, it should be a critical point, which we found, and it's the only option. And so, well, basically the price of the local brand would be this one, and the price of the national brand would be this one. But okay, again, there is a system into solving these problems. Actually, we were lucky that the function was simple enough because, well, let me put it here. Well, even after the algebra, we got something quadratic. If you take the derivative of something quadratic, you get something linear. If you take the derivative of something linear, you get something constant, which is why you got the second derivatives as constant numbers, right? After that, it all became easy in terms of evaluations. In fact, because we had to solve the system of linear equations obtained from taking the derivative of the quadratic, we went over the algebra that we know for systems of linear equations with two variables, and actually we got pretty lucky with the shape of the equations to make a simple substitution. So yeah, I mean, that would be the procedure. Again, critical points. Once you found them, the sign of this d function, of course, needing to compute the second order partials. Once you do that, evaluate at each critical point. If it's negative, it's a saddle point, which didn't happen here. If it's positive, evaluate the sign, for example, of fxx. Depending on that, either you have, if it's positive or negative, either relative maximum or relative minimum. So the next one is actually a pretty interesting problem. It's not quite as complicated as... Who has heard of the traveling salesman's problem? They haven't told you that in your business classes? Okay. That's actually a pretty cool problem, both for you and for the math people, because it's very hard to solve. Let's say that you are, well, just to make it interesting, you're a company that sells bread, right? And you have a map of how to distribute it in a city, in each convenience store, etc. So what you want to do is to find the optimal path for the distributor so that the distance traveled is the minimum. And that you do, well, you have the locations, the different locations in your city, whatever, and you want, of course, to spend less time and also less money with the gasoline when you provide. So that's a pretty hard problem to solve. It's actually not a trivial problem. It's very complex, even computationally complex. But we will do a baby problem that at least the very basic posing of the problem is related to that. So what we will do is to study 7.3.5, which is the optimal location for a warehouse. So you're a company, and the company's three most important customers are located at points in a plane, of course, we're approximating, which are A in x and y coordinates, it is 1, 5. B is the origin, and C is 8, 0. The units are in miles. Okay, we won't actually use them. So let me make a picture. So it is actually at a scale. So the point 1, 5 would be here, which would be A. The origin, which is B, would be here. And the point 8, 0 would be C. Now, you're going to establish a warehouse from which you will distribute to these three providers, which are the ones that buy most from you. And geometrically, of course, we're making many assumptions about the structure of the streets in the city, whatever. But let's imagine that you have a grid like this that's actually related to something called the Manhattan norm or the taxi norm. You want to put a warehouse in a given location in the plane. Let's say we don't know yet where. So W stands for the warehouse, and this will be related to coordinates x and y. And the question is, what are the coordinates x, y of the point W where a warehouse should be located to minimize the sum of the squares of the distances from W to A, B, and C. So the idea is that, okay, if you want to distribute to this tree, well, you're actually assuming that you have 3 different cars and you're going to 3 of them. You don't go with a single car to the tree because the path would be different. But basically you have this distance, and this distance, right? And so, formally speaking, what you want is to find the location of the point for which the sum of these 3 distances is minimal. Or you could do the same by minimizing the sum of the squares of the distances. Okay? But is it clear? I mean, if I had 3 cars, I spend less gasoline, especially because I will provide these people, like, let's say, weekly or bi-weekly. So, of course, in the long term, this would be a smart decision, if these are my 3 biggest consumers. So, we will do the posing of the problem. First of all, what we want to study, of course, the sum of the squares of the distances, which is basically the norm, or the distance from this point to the 2 other in the L2 norm. So Sxy, first you have x minus 1 squared plus y minus 5 squared. So this accounts for this distance from x to point A. Then you consider the distance from W to point B. So this is just x squared plus y squared. And then you consider the distance from W to C. So you have x minus 8 squared plus y squared, because this has, or C has, a 0 y coordinate. So, well, this is just square of distance from W to A, square of distance from W to B, and this is the square of distance from W to C. So, okay, at this point, you understand the intuition of the problem. We want to minimize this function by choosing adequately the point. There's actually a very intuitive way to solve this problem that maybe even in high school you might have seen, if you think about the center of mass of a triangle. But if not, we can obtain the same answer just by the procedure, and then I will make a comment later on how this relates to what I have mentioned. So, well, in any case, the partials, right? So, because we need the critical points. So, Sx is equal, if you think about it, 2 times x minus 1, then you have plus 2x, and then you have plus 2 times x minus 8. Then you have Sy, which is 2 times y minus 5, plus 2y, and then you have plus 2y. This one is easy to evaluate. You have 6y minus 10, if you do the multiplication. Here you have basically 6x minus 16, 18. So, the story again for this kind of problem is the same. If I want to find the critical points, I equate this to 0. This is actually a simple system. So y is equal to 10 over 6. X is equal to 18 over 6. So this is 3. Then you have 5 over 3. With eliminating the factor of 2 that is common. So the critical point in this case would be 3, 5 over 3. And, well, in order to use the second partials test, I need to compute fxx, so second derivative. Well, actually, I forgot that I wrote the function as s. So sxx. So I have it over here. Remember this. So this would be 6. Syy. Remember that I have this. So this would be 6 as well. I think it's clear that Sxy is equal to 0 because there is no y dependence on this object. Likewise, there is no x dependence on this object. So So you can confirm. And if you do the computation, actually this is constant, so this would be sxx, syy minus sxy squared. So this vanishes. Then you have 36, which is greater than 0. Okay? So, well, in fact, what you would do later on is to study sxx. But this is greater than 0, right? Because it's 6. So what you know, well, d is 36 greater than 0. Sxx is equal to 6 greater than 0. Here, you would have the minimum, right? So, well, here you have a minimum at the point 3, 5 over 3. So, well, this is our critical point, which was the first step. The second is to compute this function d, which was actually a constant, which we figured because the second partials were constant numbers. So sxx is equal to 6, this is 6, this is 0. That's why I didn't even put the dependence on x and y. Knowing that it's positive, I go to check the sign of sxx, which is positive, which tells me that this is a minimum. Now, just to make this a little bit more interesting, what happens if you add the coordinates, or if you do the average of the coordinates of these 3 points, both in x and y? The average for these would be 1 plus 0 plus 8, 9 divided by 3, 3. 5 divided by 3. Oh, surprise. Don't I have exactly this? Why do you think that happens? Well, essentially it's because you're finding the center of mass of a triangle. That's pretty much it. I mean, I'm not gonna go further into explanation, but I hope that I motivate your mathematical curiosity. But basically, if I do this average, 1, 5, plus 0, 0, plus 8, 0, divided by 3, so this would give me 9, 5 over 3, which is 3, 5/3. Well, this is actually related to something called the center of mass, right? Which is, it's part of the property of a triangle. In fact, most probably if you have a triangular shape and you put a pen right below the center of mass, it would be in perfect balance. But, well, I'm just trying to say that because sometimes you can get some intuition of the problem if you think about it in some mathematical terms that you might already know beforehand. That is not in the book. So I'm just saying that to make the course hopefully more interesting. But in any case, the procedure was clear? Yeah? Everybody with me? Okay. So we will do some concept presentation, which is how to find extreme values on a closed and bounded region. Most probably you don't know what closed is mathematically. Maybe you do, but I think that is worth to be clarified. So we'll make some definitions. First of all, so far we have spoken about relative maximum or minimum. What about absolute maximum or minimum? So f of xy has an absolute maximum at, say, a point x naught, y naught, on a region R, which is in the xy plane, if, of course, the value of the function at that point is greater or equal than the value at any other point for every point in the region. There is an equivalent definition for absolute minimum, which is that an absolute minimum occurs at the point x naught, y naught, if f evaluated at that point is less or equal than f at any other point for every point x comma y in the region. So keep that in mind. Basically, this is telling you that the point attains a maximum or minimum value over the whole domain. The region is precisely the domain of the function, or that is what is assumed. So it's not only local, but a global property, right? Local minimum, we can find, of course, from this derivative criteria. I mean, the derivatives are related to the behavior close to the point. That's why you do a tangent to the curve, but you don't know what happens after. Now, the absolute behavior means that you have to study the behavior of the whole function over the whole domain. And usually, if your domain is bounded, and let's assume that the boundary is included in that set, which means that the set is closed, you will want to find the maximum minimum value over that region, which means that either you obtain from the interior by means of these techniques of critical points, or maybe the maximum or minimum can happen at the boundary. And so the same way that in 1D you studied the optimization by finding the critical points and then the extreme values at the endpoints of the interval, you will do that in 2D, but instead of having the endpoints of an interval, you will have the boundary. The points in 1D are the boundary of an interval, but in 2D, imagine a circle, right? Or a disk. So you have the boundary, and then you have to study the interior, and then the boundary. So we will have to make some definitions, but before that, we will state a property, which is the following. So you have the extreme value property for functions of two variables. And so a function f of xy that is continuous on the closed, bounded. You know what is bounded from intuition. You might not know what closed is, but I will clarify that in a second. So you have a region that is closed and bounded. Bounded, you know, closed, we'll see. In the xy plane, attains, and bear in mind that the function should be continuous, both its absolute maximum bear in mind that it's talking about the absolute, not the local one, and its absolute minimum values on the region. So there are some conditions that the region must satisfy. These extreme values occur either on the boundary of R or at a critical point in the interior of R. So this is a 2D analog of what happens in 1D. When you look for the extrema, you look either at the interior with your derivative criteria or at the endpoints. The endpoints are the boundary and the interval. In this case, we will do a 2D study of that. So in order to understand this property, you just have to make a couple definitions. First of all, mathematically, a boundary point of R is a point C comma D such that every circle centered at C comma D contains points both inside R and outside the region, regardless of how small the radius. Okay, so I'm going to skip because I want to finish this. So, I mean, basically, let's say that you're in the boundary between the US and Canada, right? I mean, I draw a circle around me, I will have points that belong to the US and points that belong to Canada, no matter what. If I'm able to make a circle such that I'm only in Canada, I'm not at the boundary. That is clear. The definition of the boundary, of course, is the set of all boundary points of the region R. And then there is a condition, which is that R is a closed set, or it's closed, if it contains its boundary. And R is bounded if it can be contained in a circle of finite radius. So for example, just to clarify this, if you have the set of points such that the norm is less than 1, that is not a closed set. But if you have the points for which the norm